Okay, we are going. Okay, so just very quickly reviewing what we did last time because it was a pretty big deal. We had the instruction register, and the instruction register, from there we could output a value back onto the bus. That would be like the operand. Often it references a memory address, but it could also reference it could also reference it could also be like a piece of data. But then okay, great, we have the instruction right here, it's hanging out. It's 4 bits of that operator, or it's 4 bits of the instruction, the operator part. But of course, each operator actually has several parts to it, like we were talking about. Full control object for load to A from RAM is fetch, and then address in, instruction out, and RAM out, A in, right? Point being, each instruction actually takes several steps. So what do? Well, like each instruction, yeah, like a lot of them do. Although, like for example, load direct only actually takes 3. The 2 fetch and then instruction register to A, because this is the data. We don't need that step of getting anything from RAM, which is kind of interesting. So the various instructions do take a varying number of steps. So we can address this by, 1, including a counter that will only ever count to 4, really to 3, 0, 1, 2, 3. And each instruction will be like, okay, this instruction, and then the 4 steps. This instruction, the 4 steps of that instruction. And we're going to get that information from the lookup table. So 1, 2, 3, 4, that's the 4 bits of the instructions operator. And these 2 are, well, which step of it? So even though this is a 6-input lookup table, we can kind of think of it as really it's just 6 bits are coming in, but really those bits are kind of grouped in different ways. This is the operator. And this is like which step of the operator. So these ones specify an operator, these ones specify a specific step. So we could kind of do all of this with much more fancy like logic and hardware, or we could use a lookup table. And we had this same kind of idea where the idea is like the input bits have different like meaning, and we can kind of think of how the table's broken down in a special way, but it's all like abstract. It's all mental like math that we're doing here to say like, okay, how the table's broken down. At the end of the day, it's a lookup table is a lookup table is a lookup table. It's just input, output. It's a map. That's it. But we are like logically breaking it down as like, okay, well, this specifies an instruction. And then like if we're doing instruction 0001, then we're doing this step, this step, this step, this step, right? Like that's how we're thinking about it. Also, I said last time, the order of these operators, the fact that load A from RAM and load A direct are 1 and 2 is not really that meaningful. I grouped them logically. The only 2 I really had in mind, like I wanted the loads together, the saves together, the arithmetic operators together, but why didn't I do arithmetic before the loads? It didn't really matter. The only one that like I really cared about, and I didn't even really care because it doesn't really matter, but to me, I wanted no op to be 0 because it means like nothing. In the same way like 0 means nothing. So 0, 0, null, nothing, no op, whatever. That's the idea. And then also, I guess similarly, halt is 1, 1, 1, 1. F, does it really matter? No, I don't know. It kind of made sense to me to make it that, but it didn't really matter in the end. So this is the general idea. And I think I said there's 17 outputs. Yeah, each one corresponds to a specific like control signal for the different modules on the computer. The order of them do not really matter. All that matters is that this one in this bit position goes to the instruction register in. Why? Because I put it there. But it doesn't really matter. So we generated a lookup table. We did this with a series of constants. Each constant corresponds to like which bit in this whole bit string would need to be on for that control signal. And I put a big emphasis on this last time. The fact that this is the number, this one is the number 1, 2, 4. The fact that program counter out is 4 does not really matter. All that, like what really matters is the bit position. Which bit do I want on? The integer value that this binary number represents, I really don't care. I care in the sense that it's directly affected by what the bit pattern is, but really the bit pattern is what I care about. And if I want like one instruction, because I have 17 bits, if I want one instruction for like program counter out and address register in, I would just OR these bit patterns together. And it would have the two, in this case, the two bits that correspond based on whatever their bit patterns are. But of course, I use constants here precisely so I don't need to remember which bit it is. I want program counter out to be, I want the bit pattern, so 0000, 1000, whatever one it needs to be. And the address register, whatever bit pattern that is, you OR them together. There will be 17 bits, and only 2 of them will be on. The rest will be zeros. Okay? Okay, okay, okay. And I also made a point that this will give you a number. You OR the like program counter out or address register will give you a number. Again, I don't care about what that number really is. Python does because that's how it's saved, I guess, in Python. But really, at the end of the day, it's the bit patterns that matter. So 16 instructions start with the same two. Yeah, and notice that these two groups here, it's the fetch cycle. And we also did talk a little bit about the peculiarity, how like if I'm starting, like I always start with no ops fetch, even though I might not actually be trying to do no op as the first instruction. It's just the fetch is actually the previous instruction's no op that it runs. It's all the same, so it doesn't matter, but it's an interesting peculiarity there. And then in the end, we save this to a file, and we would get something that looks like this. And here I've got a fancy GIF. Zoom out. And we can see I'm doing load A, 0 step. That's the bit pattern. That's the bit pattern. That's the bit pattern. That's the bit pattern. So this will be fetch step 1, fetch step 2, instruction register to address register, RAM to A. That's what we're seeing, right? So the instruction is in here. It's saved in. And this little counter here is what's keeping track of what the microcode is. It's the microcode counter. Neat, right? So now it becomes a matter of adding this to the ESAP design. And all we have to do is, look, we already added the instruction register, so all we have to do is add the counter, this lookup table, and then connect every single one of these signals to the corresponding control signals. And then we're all set. Everything's hooked up. So this is what it would look like. I can go here, and there it is. There we go. We have, and the lookup table, if we open it up, I would have had said like file load, the hex file we generated from the Python script. And if you're like, what Python script? This one, the one, it's a very simple script. It's just the ones where we define the instructions. And you might say, that can't be all the instructions. It is. Because there's 1, 2, 3, 4, that's no op. This is the hex pattern for the 4 microcode steps of load A from RAM. You'll notice that each, like these are always going to be the same. It's because these 2 columns are the fetch. So we have 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4. So that should be 64 total things. Right? 16 times 4, or 4 times 16. Cool. So there we go. So now all we need to do is, okay, we put an instruction in here, and then the microcode counter will be synchronized with the clock, and the instruction will get executed because the control signals are hooked up. Hopefully. Probably, right? That's what we hope, at least. And how do we get the instruction into, How do we get the instruction in the instruction register? Oh, right, we have fetch. No matter what, fetch is going to happen. The program counter starts at 0. Okay, hold on. When I turn this on, what's going to happen? What do we have in RAM? Perfect. We have nothing in RAM. Okay? Now, if I start clicking, I'm going to hit the clock pulse. What should happen? Well, a bunch of no-ops are going to happen. Here's why. Fetch starts. Why does fetch start? Because no matter what, whatever is in the instruction register, it's going to be a no-op, because whenever we turn it on, it's no-op. But even if this was physically designed and I turn it on, and a random instruction is in here, which it would be in practice, the first two steps that the microcode counter will have will always do fetch. So we're going to fetch. What's fetch? Program counter out. That should start at a 0. Put it into there. 0's there. RAM out. Whatever's in address 0 goes into the instruction. Then steps 2 and 3. Fetch. Steps 2 and 3. Whatever that means. It's a no-op, so nothing's going to happen. In fact, you'll see, look. Look. It's kind of hard to see, but already I hit run. This line and this line are on. You can see. Why? Well, they better be program counter out, which it is. We follow this up. Program counter out and address register in. Or enable, but whatever. So if I start hitting run, a whole bunch of nothing's going to happen. Now, by the way, and I didn't show you this yet. Remember how I said we have that halt instruction, and we need a way to control whether or not the clock can actually have an effect on the system? That's trivially achieved with a not. I guess a not and an and, right? If halt is on, I want this to be off, and then 0 and whatever clock is 0, so the clock effectively is nothing. If halt is off, that is on and whatever clock is whatever clock is. These are those basic Boolean principles. So either way, okay, I'm going to start spamming this. We'll see the control signals change. It's just going to be fetch, nothing, nothing, fetch, nothing, nothing, fetch, nothing, nothing, because we've got a bunch of nothing in there. But it is executing the program, it's just the program's nothing. Now, by the way, I can go here, right-click. I can start a real-time clock and hit run. And what's nice about this is I don't need to press it anymore. And you can specify the frequency. I have 1 hertz. For those of you that don't remember, 1 hertz is once per second. A hertz is a per second. It's an interesting unit. If you're like, that's too slow, sure, we could do 10. And then, there we go. Cool. Pretty neat, though. All right, so, okay, including the control logic, there we go. I discussed the halt signal. But if we now look at the whole system, like we've got everything. We've got the clock, we've got the RAM and address, instruction register, control logic, control signals, the output, the 2 registers in the ALU, and the program counter. So we've got like everything. Any questions about what we're seeing here? Oops, okie dokie. So now we can actually start programming this thing. Now we were running programs on this before, but it was a very manual process. We had to go and manipulate all of those control signals ourselves, clock pulse, right? So now the system should be able to manipulate its own. So what do we want to do? Okay, so to start simple, as a demonstration of how we actually program this thing, well, first and foremost, so look, the system has a way to manipulate its own control logic. We've given the system an ability to control itself, which is always a very important thing with anything interesting. And with this, the program can be executed, like the system can execute its program entirely on its own. We just have to give it the program, and then it can actually execute and run the program on its own now. So we can write instructions into RAM and hit run. And the system should be able to do all of the instructions that we told it how to do. Now, it can only ever do the instructions that we gave it. What I mean is, there were constraints within the system about what we could do. And there's, like, I don't have hardware to multiply, for example. Now, we could do that programmatically, like in software. But the system does have constraints. And remember, when we talked about things like output register, how did that work? Well, we output from the data from a specific RAM address. Why not always from the A register? Entirely up to us. So we can write instructions that we've defined. But the point is, our system has constraints and can have certain instructions programmed, or certain instructions defined for the system. And then we made decisions on what those instructions were. And we have 16. Really, we only have 13 because we left 3 no-ops. Now we can write those instructions. Let's take a pause and review. We started, 9 weeks ago with what is a transistor? Actually, I don't even think we did that. I think we talked about true and false, right? Then we talked about transistors. Then we configured them, and we made logic gates. And from those, we made things like our latches, and multiplexers, and decoders, and demultiplexers, and programmable logic arrays, adders, RAM, counters, output registers. We learned how lookup tables can be a nice way to cheese the hardware, which is really nice. You put all this stuff together, we have a system that should be programmable. But every design decision that was made. Nothing about what we did, other than like a transistor is a thing. Obviously, I showed you, here's how to make an AND gate, but you could have made it slightly differently. Here's how to make a decoder. You could have made it slightly differently. I'm just showing you designs that we've done. But once we get like abstract enough, we really do have design decisions that we can make. Why not use a driver buffer instead of a multiplexer? Whatever, it's a design decision. Like in any program you write, the more like think back to 161. When I say write a program to do a linear search, right? Chances are everyone's linear search is going to look effectively exactly the same. And it should, right? But by the time we're done 162 and I say do the Huffman codes, everyone's solution is probably going to look quite different. Because as things get more complex, you have a lot more flexibility and tools at your disposal to solve those problems. It's the same thing here, but with hardware. So we made a lot of design decisions. And we also made a lot of decisions about what the hardware can do, what instructions can exist, and what instructions do exist and how they work. We made these decisions. We could change these things if we wanted. But we made these decisions. And now we are at the moment we can actually write instructions to have the system run itself. So let's do a very simple program. Something like output the result of 31 plus 32 and output the result of 31 minus 32. Why these two values? It doesn't really matter. I just picked them. Okay? They're easy to identify. I don't know. I like them. So in a language like Python, or in other similarly high-level programming languages, you would write something as simple as this. Print 31 plus 32, print 31 minus 32. Easy peasy, right? Well, we don't have Python. In order to write a language like Python and have it run on hardware, there's a lot of steps in between. When I say hardware too, I mean like the ESAP system's hardware. But really what do I mean is like the transistors, right? When I say there's a lot of steps between Python and the hardware, yeah, Python and the CPU, but there's already like, how many of you before this semester thought like, what are the transistors configured like in my CPU? You probably never really thought of that. You probably still don't think that because who gives a shit, right? Like it doesn't matter. That's not how I interact with I interact with my CPU, not even like at the machine code level, which we're going to be doing right here. We interact with it like through GUIs, or, you know, we're computer science people, we write programs, but that's how you interact with your hardware. There's a lot in between. We're going to be writing machine code. We're going to be writing the zeros and ones for the instructions and the data that we want to execute. Now, we're also going to do it in hex because it's slightly easier, but it's still machine code. It's zeros and ones effectively, low voltages and high voltages. If I want to say load into A from RAM, the value at address 15, I would need to tell the computer instruction 1, 00011111. That's how I do that. But that's not how you write it in Python. You don't say that crap. You say just do that. Now, I also just said, load into A the value at address 15. Presumably, the value at address 15 is something like 31. Are we done yet? No. There's a lot more steps involved. And this is a simple program, and it's deliberately picked because it's a simple program. Look how simple it is, right? Obviously, the underlying steps that the processor has to run to do this must be small, and although that's true, you'll see there's several steps involved. So our system is obviously, we can't interface with it like this, but we can still solve this problem. We can make a program that can do this. Our system can compute this, easy peasy. There's going to be more steps though. So the process of coming up with a program for our system is exactly the same as you do in other languages. It's just at what level of abstraction and what tools you have available for you in that language. We break the problem down into solvable steps that we can do, one at a time. The solvable steps and flexibility we have in Python is quite high. With us, we have 13 instructions, 16, 13, whatever. So for this arithmetic problem, here's like a pseudocode breakdown of a solution to the problem. Load 31 into register A, load 32 into register B, perform addition, save the result to RAM, output the result, load 31 into A, 32 in B, although this really is not necessary as 32 is already in there, but whatever. Let's put it there to make it explicit, right? It's always nice to have your code be as clear and intentional as possible. Perform subtraction, save the result, output the result, halt. That's how we do it. All right, so these two steps down to something like that. Now, that 31 and 32 have to come from somewhere though, right? And we are saving things to RAM, so we need RAM for that. And to be clear, I want to make sure my point is clear. When I load 31 into A and 32 into B, A, B. 31, 32, right? On line 3, I say perform addition. Well, what does that do? Well, that should give me 63, right? But where does it go? Well, based on how we made addition, and remember, we didn't need to make it like this. We could make addition, save the result to RAM, whatever, but we didn't. We say overwrite the value in A. So that becomes 63. We save the result, okay. Now if I want to do 31 minus 32, I got a problem because 63 is in A. So I have to put 31 back in here. And although here on line 7, I'm saying load 32 into register B, it's already there. So that step's kind of useless, but I'm including it because, again, I want to make it as intentional as possible. So now it's a matter of converting these instructions into the machine code. Now loading data into the registers, so we've got two options for how to load data into registers. We've got load A from RAM, load B from RAM, and load A and B directly. But because the values 31 and 32 require more than 4 bits to represent, they must come from RAM. The load A direct, we can load values in there, but the values can only be between 0 and 15, unfortunately. Well, for better or worse. I want to load 31 and 32. I can't do it. So I'm going to store those values in RAM and load the data in. Therefore, the operator would be something like load A 0001 and load B 0011. These are the load A and B from RAM. Now here I'm showing it what it would be in binary and what it would be in hex, because again, a little easier to write that, I guess. Now, the whole benefit of load, the load directs is whenever you're loading data from RAM, the instruction takes up one RAM address and the data takes up one RAM address. So that instruction kind of like implicitly requires two memory addresses. We only have 16. So we got to be careful. Load A direct eliminates that problem in that one RAM address for the instruction and that's it. We don't need that secondary memory address to store the data, but again, it's constrained. So you know there's pros and cons. So this, at the end of the day, this instruction actually does take two memory addresses because 31 and 32 must be stored somewhere. Is that clear? Cool. So where to store 31 and 32? Now, realistically, it does not matter where the numbers are stored in RAM, as long as the addresses are available. There are some interesting designs out. Well, I'll finish this point and then I'll come back to it. So in a von Neumann architecture-based system, which this is, where we have shared data and instruction RAM, RAM and data, or instructions and data are stored in the same chunk of RAM. Even though they share the same like RAM chip, it's still very common for people to like still like logically and technically physically separate the data and instructions. For example, if I start writing, look, my program starts at address 0, 1, 2, E, F, right? So I've got some instruction, some instruction, some instruction, some instruction. Maybe I have a halt here. A short little program, but I have data. I could store the data right after the instructions. Can you not see? There we go. I could store the data right after my block of instructions. Entirely fine. There's nothing wrong with that. But it's common, I definitely do it. It's common to store data like at the bottom, for example, to keep it separated. So we have RAM. Yeah, instructions and data are separated. Or sorry, instructions and data share the same RAM, but we still like to separate them. It's nice, it keeps things separate, it helps eliminate potential problems, which we will see shortly. Yeah. So anyways, so in our example, we're going to use E to store 31 and F to store 32. Why? Because, like I just said, you know, it's at the end of RAM, makes sense. So the instructions for our program would be something like this. And I'm going to write the program in a hex file. So if you remember, we need this funny little line at the top of every hex file. Fine, whatever. It is what it is. And then what's the first instruction? Well, it's going to be a hex number 1E. 1 is load into A, right? From RAM. Which RAM address? E. Now what's not shown here is at the bottom of this hex file would be the number 31 and 32. By the way, I could have, this is a hex file, I could have wrote like 0B 0001 1110, right? I could have written the bit pattern here. Maybe I should have, I don't know. But I don't know, I like the hex here. It's a little nicer, I think. What's also kind of nice is because we have like 4 bits for the instruction and 4 bits for the data, and we have 8 bits, so like, and it's hex, so we'd have 2 hex digits for the 8 bits, and it's kind of nice. Instruction, data. Or I guess operator, operand, to be far more precise. So these are the 2 instructions. The data's missing, but they would be down here, let's say. So, okay, because, what did I say here? No, because the program's in hex format, we need that, and also I could have put them in binary. Yeah, like I just said, cool. Here, the hex numbers are used for brevity and simplicity, right? I don't know. Maybe you like this better. If you do, by all means, have at it. I don't know, I just like that a little better. Raise your hand if you prefer the hex. Raise your hand if you prefer the binary. Well, to each their own. Neither of you are right, neither of you are wrong. It's the same thing, right? It's just an encoding and then you need to decode. So now what do we need to do? Okay, so we've got the value of A, 31 into A, 32 into B. Now I want to do add. How does add work? Well, it takes the value stored in A, the value stored in B, and puts it back into A. Why? Because that's what we told it to do. That's how we designed the system. At least that's how the control logic was set up. So we want to add A and B together. A, D, A, B, right? The reason it's A, B and not B, A, I actually spent a lot of time. I spent far too long, by the way, thinking about what these little 4-letter tags are. They're just tags, right? It's just like a simple little way to mean that, right? When I say 0, 1, 1, 1, or 7, that means add, right? But again, I'm using 4 little characters here to represent it. LDAR is load into A from RAM. LDAD, load into A direct, for example. ADAB, so originally I had like add B, I think. And the reason I had add B is like, well, I always know what always goes into A, because A is like this idea of an accumulator. Did I talk about accumulators yet? Accumulators are like a special name given to certain types of registers and different architectures. By the way, again, I cannot stress this enough. This is A design. The ESEP system is A design. You can make it work however you want. This is not like, oh, all computers work the same way. Every decision we made to design our system, we could have made a different decision and have it work slightly differently. It's entirely up to us. I'm showing you A design to show you how we go from zeros and ones transistors to get to programming this system. Certain instructions will have something like an idea. Certain systems will have a register that is called like an accumulator. And really what that means is like it's a register where like parts of or like the result of some operation just automatically gets stored. So A in this case is like an accumulator. A and B stores back into A. Why? Because it's an accumulator, right? So because A was this like accumulator, I said add B. Right? And where would it go? Into A, because it goes in the accumulator. That's where it would always go. Subtract would be like sub B, S-U-B-B. Why? So it would take the value from B, take it away from A. Why? Because it's the accumulator. And the idea also was like, I could have added like a C register. And I could say like add C. And that would, mess with A. But then I was like, I don't know, maybe I'll change it. So I changed it to ADBA. So it was like add B to A. Right? Because A is the accumulator. And then I finally landed on AB, which for addition might not make much of a difference for you, but it kind of might make a difference from you for subtraction. Because if I say like SUAB, you might say like, well, am I subtracting A from B or B from A? How does it work? So I don't know, I kind of did it with like the order. I would say like A minus B. But also, because it is an accumulator, I kind of had the idea of like A plus equals B, right? So like that's kind of like the idea of what I'm doing. Just to give you the method to the madness. At the end of the day, it didn't matter. It's just a label. It's just like a little tag there, that's all. But just to give you a sense of why did I do it that way. It was arbitrary-ish. All right, so add AB. That's the instructions operator pattern. It takes no operand, its value is ignored. So really, technically, I could put any 4-bit value after that instruction, and it would be entirely ignored by the system. The value would go into the instruction register, and then it never goes anywhere. It just sits there until it gets overwritten, right? So the instruction could be like 70, 71, 72, 73, 74, 75, whatever that second hex digit is entirely ignored. It has no impact on the system whatsoever. But in the spirit of making our code as clean and intentional as possible, if there's nothing, make it a 0, right? I think we can all agree that that's probably a good decision, right? Functionally, the difference between saying like 7.1, 7a, and 7.0, they're functionally the exact same thing. They mean nothing different. But I don't know, it's more clear if it's a 0. Is that also clear to you? Okay. So that puts the result into A. Then what do I want to do? I want to save A. Why do I want to save A? Well, if you remember, the output instruction took an operand, which was the memory address of the value, to output. Remember, we spent a lot of time talking about this. How should output work? Should output always output the value in the A register? We could have done that, but we didn't make that instruction, right? We made output take a memory address, and then it goes and like fetches it goes and retrieves the data from that memory address and puts it in the output register. I could have said just like output's always whatever's in A. I could have, thereby entirely eliminating the requirement to save A. I could have saved an instruction. I could have saved a memory address if we changed what our instructions are. Good, but is that a good decision or a bad decision overall in the generalizability of our system? I don't know. Maybe, I don't know. So, okay, save A. So the operator hex digit is 5. Why? Because that's what we made it. Because it was halt 0, A, load A, load A, load B, save A, save B. So yeah, 0, 1, 2, 3, 4, 5 is save A. 6 would be save B. Any RAM address, okay, the operand, we need an operand. Where are we saving it? Well, a RAM address. Which RAM address should we use? Well, really anywhere we could use. Ideally, it's not RAM that's important, right? We don't want to say go to memory address like 4 and overwrite it with this value because, I don't know, there's probably an instruction in memory address 4, right? We don't want to overwrite an instruction with something. We know we're going to need to retrieve A from RAM, so we don't want to override the value where the 31, pardon me. We know we need to get 31 back from RAM, so we don't want to store it in E because we don't want to overwrite that data. So we have to be aware of where we're saving it. Where are we going to save it? Let's put it in memory address C. Okay? Now you might say, why not D? Well, that's where I'm going to put the result of subtraction. All right? So again, what do we have? We have like load, add, save, right? That's what we're doing. I also down here I have 31, 32, right? That's where the data is, right? So far so good? Okay, load A, OXE. Load B, OX, and that's R, right? OXF. Add, save, and I said OXC, A, right? Yeah. You're following, right? Where do I want to put C? Should I put it right here over the next instruction? Because think about it, right? We want to like save A. Immediately after, I'm going to want to output something. So like output what we just saved, right? Right? Is that clear? I save it, and then I want to output the result of calculating the sum. So I should get 63, right? Imagine I said, okay, save A into memory address 0, 1, 2, 3, 4. And we overwrote this whole thing. This is a bit pattern, right? Saved in RAM. Imagine I said, oh yeah, I'll put it in 4. and I would put the result of 63, whatever the bit pattern of 63 is, right here. Would that be a good thing? Probably not. We overwrite an instruction with data. Our poor system's going to fetch the number 63 and try to decode it as an instruction. Oh, what is that even? What is 63 in binary? So 63, so that would be okay. Yeah, it's 1 less than 64. So it would be how many? What is, okay, 1, 2, 4, 8, 16, 32. That should be it, right? And what does that mean? Oh my gosh. That's actually amazing. What does that instruction mean? Come on, you haven't memorized all the binary patterns yet? All the machine code patterns? What does that mean?
3F.
Pardon? 3F, which is actually load B from memory address. That's actually just conveniently and magically the it would actually be the same pattern as that instruction, which is kind of crazy. What a funny little world that is. How about that? Now, it would still mess up, right? I didn't want to load the value 32 into memory address B again. I wanted to output this. So we would still overwrite this. So it would still be a bad thing to do. It's amusing that that happened to be the same bit pattern of that, right? Oh, what are the odds, right? I guess about 1 in 256. I don't know. So that's kind of amusing. But I guess the point is, instruction data, they're bit patterns. What do they mean? Depends on what they're encoding and how we decode it. At the end of the day, it's just zeros and ones. That was data. This is an instruction, but they have the same bit pattern. That's interesting. All right, back to this stuff. So next we want to output. We have two outputs. We have out U and out S. Remember, out U is assume the data is unsigned, and out S is the data is signed. Now, in this particular case, it wouldn't matter because 63 is small enough. It's not big enough such that the 2's complement number would be different, right? So the bit pattern for 63 is the same whether it's 2's complement or not, whether it's signed or unsigned. So at the end of the day, I could have picked either of these things. I know it's an unsigned number, so I'll go with this, right? Because whatever, again, intentionality. What does it mean? So we'll use out U. So that would be the hex value D. And what do we want to output? C, right? Why C? Because that's where I said, well, actually here. Okay, we have 0, 1, 2, 3, 4, 5, 6, da, da, da. Okay, F, E, D, C. Right? I put the value 63 here. I skipped D. I'm going to put the difference stored there. So I want to output C, 63. So now the machine code would look something like, the machine code would look something like this so far. This again is ignoring the data that I would have to add. But no value, I would not write 63 on line whatever that corresponds for C, right? Because that was calculated at runtime. This is the program at like before runtime. It's static. RAM will change once the system is running. So only the 31 and 32 would be down here. I don't write 63. The system should write it on its own. So do we have A from E, B from F, add, save, output. Now how do we do subtraction? Well, okay. We have to put 31 back into A, so we have to do load A again. 32 back into B, it's already there, so I don't really care, but let's do it anyways. But now we don't want to do addition, we want to do subtraction, so do subtract AB, SUAB, no operand, but again, we'll use a 0 because it's just cleaner that way. Save the result. This time I'm going to save to memory address D. So this should be 31 minus 32, that should be negative 1 or 255, right? Because 2's complement. Is it signed, unsigned, whatever. The bit pattern would be 1, 1, 1, 1, 1, 1, 1, 1, right? Right. If you're unclear about this, go review 2's complement. I know that it should be negative 1, so in my mind I'm thinking negative 1. But at the end of the day, the bit pattern's the same. It's my job as the programmer, though, to know what my data is. The system doesn't really know. So when I want to output this value negative 1, I better specify that I'm outputting a signed number. Otherwise, it's going to assume, or well, not assume. Otherwise, if I say it's unsigned, it's 255 because the bit pattern's the same. But it's my job as the programmer to keep track of that. And then once we output that, we halt. So here's the full program. Load from E, load B from F, add, save, output, load, subtract, save, output, halt. F0, again, it doesn't take an operand. Any instruction that doesn't take an operand, just give it a 0. It's nicer that way. Then I've got a couple of zeros here to pad it out. 1, 2, 3. And then 1F, that's 31. 2, 0, that's 32 in hex. I can't stress this enough. This is C, this is D, right? Why didn't I put 30 or 63 and negative 1 in here? Because that's what I'm calculating. That will get saved to RAM at runtime. I'm not going to, that's the point of the program. All right, since each line corresponds to one address, each line should be filled. So we actually have a bit of a peculiarity here. Now, it's, digital, if you load this up with blank lines, I'm pretty sure it assumes they're zeros. But, I want them to be zeros. I'm going to add the zeros, okay? And interestingly enough, zeros are no op, right? So 0, 0, 0, 0 is nothing, right? So that's kind of like what I mean, why 0 is no op. It just kind of makes sense, right? Just leave it alone. Now, you might be like, well, who really cares? We have a halt. These lines can never get hit. Yeah, you're right, but, nothing. It's 0, no op. It's nothing there. Therefore, the contents of these RAM addresses don't really matter. Point being, I could make these whatever the hell I want. It doesn't matter, though, because halt gets hit, the program stops, these will never get touched. Who wants to see this run on the system? Put your hands up. Come on. This is what it's all been about. This is what we've been working towards. So now, whenever we're loading data into RAM, we have to load it in a funny way. Annoyingly, you can't like right-click and be like load. You have to say edit, circuit-specific settings, advanced, preload program memory at startup, and then you select the file. Desktop, yeah, site, topics, control logic, add, subtract, output. Great. Okay. So let's turn the real-time clock off so we can, see what happens. When I hit run, if I right-click on this, I should, yes, perfect. That's our program, okay? That hex file I loaded in was the one I just showed you, right? Load, add, save, output, load, subtract, save, output, halt, nothing, 31, 32, right? We agree. So if I start running, like what's going to happen? Well, I'm spamming through this because we're running out of time. But, 63. And look. It's there now. Oh, FF is there, that's -1. And you're like, why is 63 still there? Because we haven't run the instruction, this one, yet. -1. And halt, clock does nothing now. Right? Now, for the sake of one more little bit of fun, let's put it on a 1 run. You will see that it actually takes a few seconds here, right? Like, look, it's running these instructions. Each clock cycle, you know, we're getting 1 a second, so this could take several seconds. Each instruction takes 4 seconds effectively. And how many instructions did I have? Like about a dozen or something, right? Well, finally we get 63. I'm impatient though. Let's, I don't know, 25. Cool. Now I might be in trouble if it ran too fast. I would never see the 63, but whatever. I hope this keeps you up at night about thinking about how amazing this is, right? We built this from transistors, and now we wrote a program for it. That's wild. All right, I'll see you all later.